pleasure to present our work on this seminar. Good morning, ladies and gentlemen. My name is Kryzstof Sawicki, and I'm a PhD student at the Faculty of Physics, University of Warsaw in Poland. I'm going to talk about lasing effects in two different setups, two different systems made of 2,6 materials. I will start with the topic which relates in part in polariton physics. I will show the qualitatively new 2,6 based system made of tellurides and selenides with single cadmium selenide quantum well. This system allows us to investigate 3 different types of lasing in the same sample. The second part will be devoted to polariton condensation in vertically coupled planar microcavities. So I would like to start my talk with presentation of people who were involved in the research. So the high quality sample were grown in our MBE laboratory under the supervision of Wojciech Pasuski. The TEM and EDX characterization was performed by Kamil Sobczak and Jolanta Borysiuk. Experiments and interpretation was performed in our laboratory of ultrafast magnetospectroscopy with theoretical support from Thomas Sturges. All these people are from University of Warsaw. I think everybody here knows what polariton are. They are quasi-particles emerging from strong coupling between photonic mode and excitons. So in strong coupling regime, we can describe polariton as a superposition of excitons and photons. The exciton content gives us strong nonlinearity. At the same time, the photonic content leads to very light effective mass and makes the system very experimentally accessible. So in the experiment, we can prove the strong coupling by, for example, measurement of spectra as a function of the tunic. Practically, in experiment, we can achieve that because we grow our sample with the wedge-like microcavity, which allows us to tune the energy of the mode from infrared to green region. So we basically work somewhere here in red and infrared region. So we expect several types of emission from microcavities coupled with quantum well. For a very light excitation power, mainly we observe polariton luminescence from lower polariton branch. Bosonic nature of polaritons leads to the simulated scattering of the polariton condensation in the lowest energy after increasing of the excitation power. If we increase exciton density or temperature, we can lose the strong coupling conditions, and in weak coupling regime, we can achieve the stimulated emission with conditions of population inversion, where the condition of population inversion are reached. If we further increase the temperature or exciton density, we can observe exciton dissociation and third polariton threshold, which is photon lasing involve electron-hole plasma. So far, only 1 or 2 of this lasing threshold was observed for one structure. Our goal was to achieve all 3 for one structure. So we investigate a molecular beam epitaxy grown sample with single cadmium selenide quantum well placed in the middle of the lambda half microcavity. DBR are made of zinc telluride and multi-component alloy. And here I show that the quality of the sample is very high, because we can observe intermixing mixing of the elements between the layers. So there is several advantages of this system. For example, band gaps of DBR layers are much above the quantum well and mode energy, so we avoid parasite absorption. And what is very important, the lattice mismatch in the system is very low. So let's start from emission properties in room temperature. So what we can observe is three characteristic fingerprints of lasing, which is blue shift, narrowing of the line, and non-linear increase of the intensity. If we compare binding energy of the cadmium selenide quantum well with thermal energy, it suggests that we can achieve exciton emission here. So probably it's related with electron-hole plasmas, which is n-bound electron and holes in the system. So another proof of the electron-hole plasma lasing is the measurement of dynamics, which is quite different if we compare with the polariton lasing. So after pass, we observe increase of blue shift following the excitation pass in the case of similar sample, but in a polariton lasing regime, we observe red shift after pass. In this case, it's related with the decreasing of the population of polaritons. Here is it's related more with the changing of refractive index of the layers and existence of a high amount of carriers in the system. So now we can switch to the properties in low temperature. So basically, here I plot three spectra for three regions of these plots. It corresponds to the free situation on three thresholds in the system. So the first one we can observe here. It's we suggest that it's polariton lasing. After increasing power, we can observe second threshold and third threshold. In room temperature, we observe only one threshold, which is electron-hole plasma lasing. Here we would like to prove that these thresholds are not related in the competition between ground state with the other modes. So here we observe, here I plot integration emission from higher modes and the ground state. Okay, so the first ultra low threshold is attributed to polariton lasing. Second one is photon lasing involving excitons. After passing through the exciton mode transition, we can observe electron-hole plasma lasing as a third threshold. So to get more insight about complex spectra, which we observed on the previous slides, we perform experiment with the linear polarization of detection, where we can observe linear polarization of emission, which probably are related with the shape anisotropy of photonic traps. So these modes are related with the photonic traps which arise during the epitaxial growth of the sample. So now, to get more information about this type of photonic traps, we perform tomography of K-space. So here we can observe full reconstruction of K-space achieved by measurements of K-resolved spectra as a function of position of the lens before the slit of the monochromator. So this three-dimensional image we can interpret as a photon energy as a function kx and ky. Here we observe these discrete modes. So let's focus on this shape. So these discrete modes are very similar, like in the case of micropillar microcavity, which we treat as a proof of the existence of photonic traps and the emission from these photonic traps. So now what we can do is I plot a cross section of the the lowest modes, and the angle distribution of the modes are independent of the polarization of emission. So it's very similar, like in the case elliptical microcavities. So the shape anisotropy of the photonic traps determine the radiation pattern of these modes. So here to compare the effective size of the photonic trap with the micropillars etched from microcavity, planar microcavity, we etched 9 micropillars with different diameter. So here is the close-up on the one of them. And if we look for the emission from micropillars, we can observe a different distance between the modes. And now we can compare it with typical spectra from photonic traps. We checked 33 photonic traps, and typical effective size of the microcavities is similar, like in the case of micropillar with a diameter 3.5 micrometer. So it brings me to the summary of the first part of my talk, where I show qualitatively new cadmium selenide and Telluride microcavity, which allows us to observe free lasing threshold and free thresholds in the emission and emission in room temperature. And I show that in emission are involved for photonic traps in the microcavity. So let's move to the next part, in which I switch a bit the topic, and I focus on polariton lasing from multi-level exciton-polaritons system. This type of systems offer an attractive platform for studies of nonlinear optical phenomena such as Bose-Einstein condensation or parametric scattering. In particular, they open the possibility of constructing optical lattices, enabling three-dimensional polariton hopping. So typical, if we have one microcavity and one emitter, we can achieve a two-level system, which was discussed in the first part of my presentation. Now we have the simplest one is two microcavities and two emitters, which leads to a four-level system with four polaritonic branches. So multi-level systems have been realized in vertically coupled planar microcavities, mostly in linear regime. The non-linear regime was addressed in the context of resonantly driven parametric scattering, like momentum degenerate parametric scattering, with the transition of the polaritons in the same k-vector, or energy degenerate parametric scattering with the transition in the same energy. But until now, there has been no research on degenerate parametric scattering induced by non-resonant resonance stimulation. So we run this type of sample with two microcavities and two sets of quantum wells placed in the middle of the microcavities. So it's the sets of three quantum wells, cadmium, zinc, telluride. Here we can prove the quality of the sample with the, here we observe, we can see three quantum wells. And similar like in the case of first structure, we can tune the energy of the modes, photonic modes, by the changing of the position on the sample surface, because the microcavities are wedge-like. And what is more important here is that the gradient of the thicknesses of the microcavities are the same. So we can tune the adjusting the position of the sample, we tune the energy, keeping the same value of cavity-cavity coupling. So now here we can observe non-resonant case where the here we have two photonic branches and quantum emission from quantum wells. If we change the position, we can observe four polaritonic branches here in the resonance conditions. So now I plot here three frames from this movie. So we also can describe this emission by the model, theoretical model, which is the n-coupled oscillator model adapt to multi-level system. So Hamiltonian of this system looks like this. So it's four component. First one describing uncoupled photonic mode and quantum well excitons. Second one, coupling between photonic modes and quantum wells in the same microcavity with the coupling parameter omega. Coupling between photonic modes with the coupling parameter kappa. And the last one is the coupling between excitons from different cavities. In our case, we can neglect this, the last term. So we, in our case, we have a four-level system with two microcavities and two quantum sets of quantum wells. So here is the four-level polaritonic systems. What we have here is the reflection spectra as a function of position of the sample. As we can observe here, this model describes very well the experiment. From the fitting, we achieve coupling parameters. So now let's focus on the lowest polaritonic branches in the very low detuning, where the excitonic content for the lowest polaritonic branch is about 7%, and for the second one is 27%. If we increase the excitation power, we can observe at the beginning emission mainly from the upper level, and much weaker emission from bottleneck of the lowest polaritonic branch. Further increasing of the excitation power leads to the change of the dominating line, the emission. So here I plot situation below threshold and above threshold. So here was once again emission from upper one and emission from lower in the bottleneck, and after passing through the threshold, emission from upper and lower, but the lower is more intense. So these two images correspond to the full evolution of the spectra, which I plot here. So basically we can observe crossing of the lines and saturation of the upper level. This threshold is assisted by narrowing of the line and blue shift. For the upper level, blue shift is higher due to higher content of the excitonic fraction. This image is this evolution is described by open dissipative Gross-Pitayevsky equation, in which we assume that non-resonant pump creates inactive reservoir, which is transferred to the upper active and reservoir and lower active reservoir. These reservoirs are described by rate equations written here. And after polaritons from upper level and lower level relax to the minimum of the polaritonic branches, and dynamics of the condensate at the minimum is described by Gross-Pitayevsky equations. We also include the term describing transfer from upper level to the lower level. So to answer the question, how it's possible to achieve two condensate in the same place but in different energy, we perform time-resolved experiment, which explain us that following the excitation pulse, we observe at the first step lasing from lower level, and after decay of the lower level, emission from upper one. The order of the emission below and above threshold are the same, but the dominates line is reversed. So our model describes also the dynamics very well, and from this modeling, we can figure out that the transfer rate from active reservoir to condensate determines the order of the emission. And moreover, the oscillation in the emission and decay are a consequence of the presence of common reservoir and competition between polariton population build-up. So In the last part of my presentation, I will show that effect which you could observe on the previous slides, which is parametric scattering under non-resonant pumping. And so this energy degenerate parametric scattering we observe in the emission in the same energy as a condensate on the upper branch. So it's the discrete points in the lowest polarity branch in the high K value. So this non-resonant excitation is very beneficial because we have spectral separation of the excitation and measured signal. So if we look on the integrated image of this plot, which is here, integrated in the photon energy, we can plot kx, ky image, which is a radiation pattern. And here in the middle, we observe condensate and scatter pair of the polaritons here. So if we check emission from the scatter place as a function of K0, we can observe here linear dependence and strongly nonlinear dependence here, which we interpret as in the first part Rayleigh scattering, and in the second part parametric scattering of the polaritons. So it brings me to the summary. We have observed non-resonantly driven polariton condensate and dual wavelength polariton lasing in 4-level polaritonic system. Emission from the lowest polaritonic branch shows nonlinear behavior with the common threshold in input-output characteristic. I showed that the formation of condensate in the upper branch triggers energy degenerate polariton parametric scattering from upper to the lower polaritonic branch. And the time-resolved experiments prove us that the condensates on the two polaritonic branches do not coexist at the same time. And open dissipative Gross-Pitalski model describe very well integrated, time-integrated measurement and time-resolved measurements. So thank you for your attention.
Thank you very much, Krzysztof. So I hope you're okay to take some questions now.
Yes, yes, of course.
Great. So let's start. Let me start with opening the discussion. So are there any questions from the group? I can't see any.
I have one. Can I ask?
Yes, Anton, please go ahead.
Yeah, thanks a lot, Krzysztof, for the nice talk. I have one question to the very first part. If you can show the experimental dependencies with the multi-thresholds there.
Yes.
Yeah, here, I'm a bit wondering why you actually observe such a small line narrowing above the threshold. At the first polariton condensation threshold is the first threshold you basically relate
yes.
condensation, and it's surprisingly low, almost no line narrowing at all. So it is a bit. How do you understand it?
Yeah, I think it's hard to explain. It's the typical behavior for this sample. So maybe it's related with the ultra low threshold. So it's a very low number of polaritons there. and this narrowing of the line is related with that. Yeah, but it's a typical behavior for this sample.
Okay.
The Q factor of the sample, by the way.
For photonic traps, we estimate that it's maybe 2000s. For a planar microcavity, it's 500. So it's rather low.
Okay. Yeah. All right. Thanks. Also, I have the question to the very last part. Is actually very interesting physics there, especially to the mechanisms. If you can comment a little bit to the microscopic mechanisms for the transfer, the density of from upper level to the lower.
Mm-hmm.
I see you put some phenomenology into the Kryzstof there, but yeah, do you think is there any? Yeah.
Okay, so the parametric scattering is the mechanism.
Sorry, not parametric scattering. Actually, the direct term. You also, yeah.
Okay. So okay, I see. It's hard to explain. It's in this term we take into account all possibility transfer of the from the upper level to the lower level. So basically it's the, for example, transfer parametric scattering, but also maybe transfer with photon emission. So it's all processes which leads to the transfer from upper level to the lower level.
All right.
But it's hard to say which one dominates here.
Yeah, because the parametric scattering goes on the other energy, not to the ground state.
Yes, but polariton scattered here relates to the lower, the minimum of the lower branch.
I mean, as a secondary process after the parametric scattering, yeah.
Yeah.
Okay. Okay. And do you think there is a chance you have some sort of optical vibron? Optical phonon there, which would match the gap between the upper and the lower.
Yeah, for this material is I think it's the phonon energy is higher, but I only it's hard to say what is the really mechanism of transfer. Yeah. So.
Okay. No, it's all right. I'm curious if you have some.
But what I can say from the simulation when we try to fit this intensity input-output characteristic, in the case Kryzstof equation without this term, we can achieve the saturation of this curve. So probably it's some mechanism responsible for that, but it's hard to say which one.
Okay, thanks a lot. And you also, somewhere here, you also mentioned that you have, since you have in your time dynamics, you have sort of oscillations, then you conclude there should be some common reservoir for them. Could you specify what kind of common reservoir you recommend?
It's common because we pump here in the high energy, and we here split the reservoir for a upper active reservoir and lower active reservoir. So by a common reservoir, I mean inactive reservoir in high energy.
But one is located in one cavity, let's say, another in another reservoir located in the other cavity. Is that right? Or?
I think it's better to say that the inactive reservoir is in the high energy, and upper reservoirs are in the polaritonic branches in high K.
Okay, I'm just a bit hard to understand how physically the, let's say, electron-hole pairs from one cavity can, somehow contribute to another one through which mechanism? Through the cavity photon coupling, or through how?
Okay, so I would like to mention that we consider the polaritonic branching as a coupled mode, and photonic mode are coupled, even if we have non-resonant case with quantum wells.
Yeah, but electron holes reservoir are not coupled, as I understand.
Yes.
So you pump two reservoirs, basically, if that's correct, or I misunderstand something.
I think I need to think about it more.
Okay. Yeah, and also to this picture, I also have a question regarding the time resolved dynamics. You said that there is a parametric scattering, which is most likely the process that transfer the particles from upper to lower branch.
Yes.
Also, there is a here. Also, it seems I'm wondering if you try to resolve in time space the emission k equal to 0 at upper and discriminate from the emission at k not equal to 0 from the lower branch. If you try to resolve these two emissions in a strict camera, from the have you
okay. Could you repeat the question?
Yeah, sure. Have you tried to look on a strict camera the time response of the emission at high K, which is out of parametric scattering? How does this, is it at the same time, is it simultaneously present with the upper branch? Or?
Okay, so emission from high K and emission from K0 from upper branch is very similar.
Okay. I mean, they're coexisting at the same time, right?
Yes, that's true.
Thanks a lot. This is very interesting.
Thank you.
This is very interesting, physics. Yeah, thanks.
Yeah, thank you for questions.
Thank you, Anton. Maybe before we move on to other questions, if we go back to the schematic that you have with the Grosspitaevsky equations, following from Anton's question, the transfer from the upper condensate to the lower condensate, it is not energy conserving if you do not consider some other particle that will absorb the energy. So have you characterized this kind of double condensate, upper lower condensate dynamics for different detunings, which practically control the energy splitting between the upper and the lower condensate? And has this affected this term that you have, RUL, which practically tells you how efficient is the transfer of population from the upper to the low, in order to understand where is the energy going? I mean, are you coming closer to a phonon resonance? So what is, what takes the energy away for you?
Okay, so thank you for the comment. Yeah, we basically measure this emission, this lasing emission, in similar detunings. So maybe for different detunings we can check this. Yes.
Mm-hmm.
Yes.
Have you done it? Have you measured it for different detunings?
Yes, but it was very difference between the tunings in our measurements. So I think we need to check in the for a big difference between the tunings.
Mm-hmm. Okay. Also on the same topic, have you tried to model your results by taking into account only one active exciton reservoir? Because just to go back to the discussion, indeed your system is coupled. So an exciton in the quantum well of one cavity or the other cavity is practically an exciton in your system. The polariton branches do not distinguish if the exciton is one in cavity number 1 or in cavity number 2. So I'm 100% happy with the approach that you take into account only one inactive exciton reservoir. But then I wanted to understand, if you take only one active exciton reservoir, can you model the dynamics that you observe? Is it necessary to take into account two active exciton reservoirs, one for the upper branch, one for the lower branch?
As far as I know, if we consider only one active reservoir, we cannot achieve oscillation in the decay of the emission. So it's to achieve this oscillation, we need to two modes of the reservoirs. So, but
when you refer, if you go to the next slide and you show
yes.
the lower graph, right? When you refer to oscillation in your data at around 30 picoseconds, there is a hint of an oscillation for the upper branch. It appears, goes down, and it reappears. But in your model, there is no oscillation. There is only population transfer, isn't it?
Yes, yes. Yes. So
when you refer to oscillation for the model, to what do you refer? Do you refer to the population transfer or something that we do not see here?
No, it's only population transfer and competition between condensate to in buildup.
Okay, thank you. So let's move on to other questions. Tamsin, I saw you have raised your hand.
So can you go to the streak measurements at the beginning of the talk somewhere? Sorry, there's a lot of slides back.
Which one?
So when you had the triple threshold, the streak ones, so there were 2D. This one, yeah. You have like a small revival in everything above threshold at 300 picoseconds, and I was wondering if you knew what that was.
It's hard to understand the question because the voice is very the quality of the voice is.
Tamsin, can you please repeat the question?
So at 300 picoseconds, you have a revival of the luminescence in the final three images.
Here, yes.
Yeah, these.
Is an artifact. It's a measurement artifact, so it's not important.
Mm-hmm. Okay.
Okay. Yeah.
Are there more questions? I can't see your hands, but if you have a question.
Yes.
Helgi, sorry, I saw Helgi unmuting his microphone first. So Helgi, please go ahead first, and I will come to you, Sergey, later.
Just, I was thinking about the questions from Anton earlier, and I'm not quite understanding why were we discussing about electron and holes transferring between the two cavities. Why was this? Because I didn't see this appear anywhere in the model. So why? So Anton, can you maybe tell me why we were discussing about this?
Maybe I will show the picture.
Yeah, just I got that inactive reservoir is actually what we pump initially, the electrons and holes. The initial pump, the initial charges we pump.
Yeah.
Yeah, at the end of the day, it turns out that this is the inactive excitons reservoir, which feeds the inactive reservoir, as I understand, right now.
Yes.
Okay.
It's a strongly coupled system, so you don't need to take into account two exciton reservoirs. And very nicely, Krzysztof, you told us that you did not, in the previous slide, you did not take into account exciton-exciton coupling, so coupling from two different different quantum wells. So this is excluded. Is there a follow-up to this question?
No, I was just a little bit confused because I mean the model is like it's like, you know, you describe the reservoirs like when you have multiple quantum wells in a single cavity. It's like you just
It's exactly the same. Yes.
So yeah, no, okay, then yeah, maybe one question then. So when you have this energy degenerate parametric scattering and you have condensates in the two branches, have you do they possess any coherence properties? Are they if you measure the coherence between them, will you see something, or are they completely incoherent objects that just leak particles from one to the other?
Okay, so we have tried, but we didn't see it. But I think it's possible to observe. So if we try harder, I think we will see it.
Okay. Yeah. No. Thanks.
Thank you, Sergey.
I had very similar question to the first question of Anton about the narrowing at for the case where you observe triple threshold. The question actually, my question was, can you explain why the threshold, the line width for the second threshold is significantly smaller than, so that it decreases even further?
Okay. So you mean why here it's small and here is much higher?
Why it decreased for second threshold with respect to the value which you obtained for the first threshold?
Mm-hmm. So I think it's related with the if we have polariton lasing threshold, so we have two modes, one from quantum well, second one from photonic mode. Here we have only photonic content. So I think it's related with that.
Mm-hmm. And then in the range where your yellow area covers the right part, you again start seeing the broadening.
Yes.
To what process this broadening corresponds? So in terms of, like you explained, this transition from narrowing for first threshold and to the second threshold.
Okay, so if we consider narrowing of the line as a increasing of coherence in the system, so here we have decoherence related with the dissociation of the excitons. So by yellow bar, it's marked mode transition.
Mm-hmm. Thank you. And somewhere around here, you have shown tomography, which was blue colored. Yeah. So here you have some case which are just not measured, or so that it's not full paraboloid. which you show.
Okay, yeah. You mean in high K? There is, yes. So it's for one polarization. This image is showing for only one polarization.
Thank you.
So in the opposite polarization, we have opposite case, which we can see here.
Okay. Are there any more questions? So, sorry, Anton.
But can I have a last one? Yeah.
Yes.
Back to parametric scattering. Have you tried to look at the correlations, G2 correlations between left and right emission?
Mm-hmm. Yeah. So we have tried, but it's very hard to measure it. So we didn't see any correlation, but I think it's possible to observe it.
How have you tried? I'm curious.
Yes. So we try to correlate signal from this point and this point, and also from point in the middle with point on the lowest polaritonic branch. So it's very hard to, because as we can see here, it's very inhomogeneous condensate. So it's hard to choose the correct place from which place it's scattered.
Mm-hmm.
So I think it's a very hard experiment, but I think it's possible to observe it.
Yeah, I assume you tried the standard HBT or standard HBT measurements.
Yes.
Yeah, all right. Not just those on a streak. This is just.
No. I mean, yes.
All right. Thanks.
May I have a
Dmitry
question? Very short one. Maybe I missed something, but I just wondering what was the origin of the photonic traps you mentioned in
Okay.
part of the topic. Is it something like random defects, or it purposely made in the structure?
Okay, so maybe I show it here. So basically, 2,6 materials are inhomogeneous. The process is very hard because the temperature of growing of the selenide layers are much higher than for example, zinc telluride layers. So changing of the temperature increase the inhomogeneity in the sample. So what we can see here, I don't know if it's you can see here, is dislocation. So this.
I see the pointer. It's in.
Okay. So, now can you see it? So here is the dislocation, maybe here. So during the architectural growth, we create dislocations, and these locations acts as photonic traps in the sample.
Yeah, thank you. And so this 3 threshold you observed, is it somehow connected with this with a particular like random appeared trap, or this is not, and the traps are only give you this few peaks, few black peaks on the.
Okay, so this behavior we observe only for photonic traps. So we guess that the photonic traps increase Q factor of the microcavity, and it's possible to observe only for. So if you check the emission from the sample, only discrete points on the sample. Only in the discrete points you can observe a strong emission.
Mm-hmm.
So it's related with the photonic traps. and for sure it's a measure for photonic traps, not for clear planar cavity. Yes.
Okay, thank you.
Do we have any more questions?
If I may.
Please.
Yes, thank you for a great talk. I have a question about time-resolved measurements. Can you explain the shape of the curve that we are observing and why there is a second peak? And also, I believe in the model you have a second peak in the rise time of the emission.
Okay, so you mean why we have two curves here?
No, above threshold for the lower.
Here, yes.
Yes.
So why, for example, in the red curve, we have
to interrupt you, Krzysztof, sorry to interrupt you. I think the question refers to the lower, to the black curve. So Stepan is asking why, not in the model, but on the experiment, but also on the model, there are two peaks, if you like, in the time-resolved PL of the lower condensate above threshold.
Yes, exactly.
So here, two peaks. Yes, here, yes.
Yes, both on the model, but more explicitly is it is more pronounced in the experimental data above.
Okay, so we think that this behavior is related with the competition in build-up. Because we have one common reservoir and two condensates on the two polaritonic branches. And this competition between condensates are responsible for the two peaks in the decay of the emission.
Thank you. Are there more questions?
Sorry, I have a follow-up question for this one. So there is on the upper right figure in this slide, there is also a small oscillation for not only for lower but for an upper polariton as well, for upper condensate. As I understood, yes, there is a competition mechanism, a competitive mechanism for the lower condensate, but for the upper, what could be the reason for this oscillation, for this small peak in front of one, which is not observed in the model?
I think the reason is the same, because if we, for example, if we imagine how looks like population of inactive reservoir, so if we have emission from, for example, lower one, the population of reservoir is at that moment lower. So I think, I mean, this type of competition between polaritonic branches and polaritonic condensates, but in fact, it's in model we can observe it.
So basically, it means that, for example, in model you treat your inactive reservoir as infinite, and in experiment it should be some kind dependent on the rate transfer energy to the lower, for example, and it somehow changes the population of the upper one. All right,
we assume that inactive reservoir have a part of gamma which is decay, so it's not infinite. So it's also decay of the reservoir included.
Okay, thank you, Dimitri. Any more questions? Well, I have a question before I see another hand, which goes back to the parametric scattering. And here you attribute the ring emission that you see to parametric scattering, which is a plausible mechanism. Have you recorded the emission intensity as a function of pump power for the signal and idler, only for the high wave vectors, to show if they are, what is the dependence and if it is different to the dependence that you get from the condensate?
Okay, so I didn't prepare this image here, but yes, we measure it. So I think it's harder to explain the mechanism in this picture, because we observe also we observe the two types of scattering here. So one is the Rayleigh scattering, and second one is the parametric scattering. So it's hard to distinguish this.
Exactly, this is my point. How can you distinguish between Rayleigh scattering in a strongly disordered microcavity, which would give you this kind of ring emission that you have, to parametric scattering?
Yes, so we think that if we, what I show here, if we plot emission from scatter points as a function of K0, the first part is the Rayleigh scattering, and second part, nonlinear, is related with the parametric scattering based on literature, for example.
Sorry, so these are data, and KR, I can't see very well. You have K.
Okay, okay. So it's the KL and KR are the points. So this one is KR and this KL as a function of K0, which is here.
Right, now it is clear. So clearly you have a nonlinearity in the buildup of the parametric process, and you compare it to the intensity of the condensate, so it is present. Very nice. And the non-uniformity of the ring is attributed again to disorder?
Yes.
Right. Okay, thank you. Are there any more questions that have come up? No, just a pedagogical question, Krzysztof. When you are showing the first dispersions for the double cavity, where you have your double cavity,
yes,
and you show the dispersion, you have, if you can go to this slide, I saw that you have X1 and X2.
It's too far. Okay.
Yes. So you have two excitons in the system. Yes. So are your excitons degenerate, or there is a small splitting?
I didn't show it, but in the microcavities there are little different type. One of them is the cadmium zinc telluride, and cadmium zinc telluride doped by manganese.
So there is an energy shift, the small energy shift between electrons, yeah?
Exactly. This energy shift is related to the dopant of the manganese in one of the sets of microcavities.
Okay, thank you. So if there are no more questions, I would like to thank you again very much for joining us today. This is the tradition. We have lots of questions at the end of a talk because we really try to understand. So I hope you don't mind.
No. Thank you. Thank you for your questions.
Okay. So thank you everyone for joining. And Krzysztof, if you can stay on the line and we can carry on with the discussion. Okay. Have a good day.
Okay.
Hello. Thank you for the talk. Very nice, very nice results. So let me just turn off the recording. There's no point anymore.